to the second lecture in Module 10 on grid generation and aspects of real-life CFD analysis. This is also our last lecture in the course. Just a brief look at the module outline. We discussed in the previous lecture a brief introduction to grid generation, and today we will have a look at the aspects which are important in practical CFD analysis. Let us have a recapitulation of what we did in previous lecture. We discussed formally the definition of grid, classification of grids, and we had a look at the fundamental steps involved in grid generation process, and then we discussed briefly about two primary grids and their generation, that is structured grid generation processes and the methods for unstructured grid generation. So, these were topics which we briefly touched upon in the previous lecture. For the details you will refer to the appropriate literature. In the second lecture in SMART concluding module, we will look at some of the aspects which are required, which we must keep in mind while applying CFD analysis for practical engineering analysis or research purposes. So, we will primarily look at two aspects. The first one is what we call verification and the second one is validation. Then we will briefly touch upon the methods which are used for complex geometry flows, and the last topic which we are going to touch upon is the parallel implementation. So, let us start with the first topic, that is verification and validation. The CFD analysis, whether by homegrown software or using commercial software, would give us some numbers in response to the solution which we seek for the flow field variables. Majority of the CFD solvers will give us these numbers and their beautiful representation using various post processing tools, but do these numbers mean anything? Are they any useful? And that is wherein this process of verification and validation is very important. And let us remember that CFD simulation represents an approximation to a real world problem. We have made at different stages of CFD simulation many assumptions. Okay. So, approximations are involved in each step of numerical simulation process. We approximate our constitutive models, we make certain assumptions and we derive a mathematical model. The boundary conditions also may not be represented exactly the way they occur in a physical system. So, this approximation involved in the boundary conditions. Then we have already seen that whether we choose finite difference, finite element or finite volume discretization procedure, there is an approximation involved. This discretization process yields a system of algebraic equations, and these systems cannot be solved exactly either on the computer which has got finite precision, and moreover we would be working with most of the time with iterative solution processes. So, there are some errors or approximations involved in these iterative solution of the discretized system of equations. So, a CFD analyst must be aware of each of these approximations to be able to interpret the results of analysis properly. And these errors in the solution must be identified, and we should be able to quantify them for use of CFD results in engineering analysis and design. We can say that what confidence we have in the numerical results or approximate solutions which we have obtained, what are the error bounds, and we should ideally be able to get a quantitative bound on the errors in our numerical simulation. Only then we can fruitfully or confidently use these CFD simulation results in our design process. Now, this quantification process should be done in two steps. The first is called verification and the second one is called validation. For further details you can refer to an AIA document published in 1998 and more recently a similar document prepared in Europe called Arc of TAC. Now, let us discuss what we mean by verification. So, verification stands for quantitative estimation of the closeness to the numerical simulation results to the exact solution of mathematical model. So, in our CFD analysis, what we did, our first step was we obtained a mathematical model, which was in the form of a partial differential equation or in the form of an integral equation in our integral formulation. Now, then we applied a discretization process which had its own built-in approximation or errors involved there, and then we solved it using an approximate numerical solution process. Now, we would like to quantify and we would like to say that the final approximate solution which we have obtained, how close is it to the exact solution of the mathematical model, if that were possible to obtain. So, that is what is verification, to get a quantitative bound of the closeness of the CFD results to the exact mathematical solution. Now, this particular process would ideally require that we should be able to compare the computational solution or CFD solution with known analytical solution. In fact, that is not going to happen most of the time, specifically if you are trying to solve Navier-Stokes simulations in complex geometries. Exact solutions, exact analytical solutions are simply ruled out. So, in that situation, our only recourse is what we call high accuracy benchmark solutions, which have been obtained using specified numerical simulation processes with very, very fine grids. So, there are two options for us. If we have analytical solution to our problem or a simplified version, try first on that simplified version and see if our numerical simulation process matches with the analytical solution which is known to us, or then compare our solution with a high accuracy benchmark solution to complete the verification and get a quantitative bound on the accuracy of CFD results. Now, for this verification process we have to follow a few steps. The first step which we commonly use is what we call grid independence test. That is to say, the numerical grid which we have used in space or in time, our solution should not be dependent on the choice of the grid. We should be able to get a numerical solution which will not vary if we change our grid significantly. So, this is what is known as grid independence test. So, what do? Perform a careful grid independence test in spatial as well as temporal domain by systematically refining grid size and time step used in CFD simulation. In this step, we take a sequence of refined grids, a coarse grid, a medium refined grid and a very fine grid. So, we will take at least 3 grids in space as similar steps we have to perform in time, and then obtain a solution with each of these combinations and say if we are able to get a solution which does not vary by refining our grid any further. So, that solution would be what we call a grid independent solution. So, this step would yield a grid independent solution, and the next thing is comparison with a benchmark solution. This benchmark solution could be an analytical solution if it were available, or it could be a high accuracy benchmark solution which may have been obtained using some other numerical scheme and a high resolution grid. So, there are 2 fundamental steps involved in verification process: establish grid independence and then compare our grid independent solution to the high accuracy analytical solution or numerical solution. Now, please note that this verification process provides us a quantitative measure of the accuracy of CFD solution with respect to the mathematical model which we have used in CFD analysis. It does not give us an estimate of the accuracy vis-a-vis our real life problem. Okay. We have just established that how close the CFD solution is to the exact solution of our mathematical model. So, that is what we establish through verification process. So, let us have a look at one simple example which we have done in our group. CFD analysis of a Francis turbine, which is a hydraulic turbine. So, let us this is geometry and grid, which will, it can give you some idea of the way the grid was generated. You can easily say there are few sub blocks in which the geometry was decomposed before attempting to generate the grid. So, there are separate grids generated in each of these subdomains and they were merged together to obtain the overall grid for this turbine. And then for verification purposes, there was sequence of grids generated. The crudest one was, which involved 400,000 elements, then 700, 1900 and 2700. So, we have taken 4 grids and we obtained an estimate of the torque which this turbine produces and the efficiency of the turbine. Now, these two are the scalar parameters which are obtained as integrated effect of the numerical solution. So, these are easy to use for the verification purpose to establish the grid independence. So, what we can say, if with the grid size of 1.9 million or 2.7 million, with both of these there is no change in the numerical result. Similarly, we also plotted the results for these with these 4 grids for the hydraulic efficiency of the Francis turbine, and once again we can say that whether we use 1.9 million grids or let us say close to 2 million grids or 2.7 million grids, the results do not change much. So, that establishes that look, the solution which you would obtain with either of these grids would be grid independent solution. So, this is typical way of performing a grid independent solution. Take a pretty coarse grid, find out the solution, then take a finer grid, then still finer grid and a very fine grid. And in design iteration cycle we would use either of these 2 finer grids which have established the solution does not vary with use of either of them. Next, let us have a look at the validation process. In the validation, it is a process of determining the closeness of approximate numerical simulation to actual real world problem. So, we will forget about what the mathematical approximations were made. We want to see how close our CFD results are to the actual field problem. So, this definition is what for the validation process has been proposed by AIAA in 1998. And the CFD simulation should ideally be validated with experimental measurements which are performed on real systems or its physical model, but this is the ideal situation. In real life, it may not be possible for us to perform high accuracy experiments on our real systems. Some of the systems, for instance, we are performing or we are using CFD analysis in the design stage, our real system still does not exist, this prototype is yet to be made. So, we cannot perform the experiments even if we had all the facilities in the world. Then what do we do here? So, in actual real life application, it may not be possible to obtain detailed experimental data for the physical system which we have analyzed using our CFD simulation. Then what do we do? In such cases, the validation is normally done by comparing the numerical simulation with experimental data obtained for a subsystem, that is a small part of the system. If we have experimental data for that, use it for validation purposes. Now, further details of validation process, please refer to the guidelines of AIA published in 1998, and its summary you can also find in the CFD book by Versteeg and Malala published in 2007. Now, let us have a look at few examples of validation process. The first one would be our CFD analysis of Francis turbine, which we had earlier seen in verification stage. So, we had some experimental data available on the turbine provided by our industrial partner. So, the experimental data were available for head, power generated and the efficiency. So, the blue line here, these represent our experimental data, and the red and green, there are 2 sets of numerical simulation results based on CFD analysis. The first one corresponds to what we call unsteady runs. So, turbulent flow here and in this Francis turbine. So, we have used Reynolds average Navier-Stokes simulations. So, red one is based on what we call unsteady runs, and the green ones are the results obtained using steady state runs simulations. So you can easily see there is some difference, but the trend is fairly similar to what is shown by the actual physical experiments. The same trend could be seen with the power versus discharge curve. Again, our CFD results, they give us a lower values of the power generated compared to the actual experimental data. In a sense, it's a good thing that we are on the conservative side. Next, about the efficiency, the experiments predict an efficiency of close to 92%. The CFD results give us an efficiency around 90% using both unsteady and steady state simulation. But it gives us some confidence that we can go ahead and use our CFD results for further analysis or design modifications, because we get fairly close estimate of the efficiency, power generation, or the head produced by the turbine. And please remember, even the experimental data may not be exact. We did not have the bounds to plot here, but remember, this experimental data would also have certain uncertainties involved because of the errors in the measurement process. So, the differences which we see here in the efficiency there would be termed as acceptable. Now, next one is a very high accuracy DNS, a direct numerical simulation, which we had performed on a flow over a rough bed channel. Now, to validate our direct numerical simulation results, we had compared our numerical results with available experimental results of similar type. Here we have used a parameter which is called reference Reynolds number. So, our simulation was based on reference Reynolds number of 102, and we had taken few experimental results with the varying reference Reynolds number of 45 and 92 and 208, and we could see a similar trend. Okay. Not just that, we had this log law of the wall for the same reference Reynolds number, and we can say in the logarithmic region it's very difficult to distinguish our DNS results with the log law. And similarly in this region, for the corresponding or the close values of Ks plus, the DNS and experimental results, they are very close by together. The one which is far off, that is that was done long time ago in 1971. So, it contains lots of errors. So, this gives us confidence that our DNS is actually very accurate. Not just that, we can now use the DNS results which we have got close to the reference elements. The solid line here, vertical line, tells us the top of the reference elements. So, say that now the results which we got close to the reference elements or inside the reference elements using DNS are close to the exact values which we can expect. No experiments can be performed here, and we, even if we can use certain probes, they will give a very erroneous data. So, that is why once we validated our DNS results far away from the reference rough surfaces, then we can confidently use our DNS data for use as exact results for our problem. So, we need to validate not just the RANS simulation results, we have to validate the numerical simulation results opting with large area simulation or even with direct numerical simulation before we can confidently say that yes, our DNS data is very accurate and it can be used as a very close approximation or almost an exact solution of a flow problem. Our next topic which we are going to pick up today for the real life analysis is the methods for complex geometries. Few of them we have already seen earlier in our grid generation process. So, this is more or less a recap of what we have done earlier, and why we need to recap it or discuss it again is that the practical flow problems invariably involve complex geometries. So, we should be able to handle these geometries in a numerical simulation process, and for these problems the most important aspect is generation of suitable grid. And we also discussed yesterday this is one of the most demanding aspect of CFD modeling in industry when we are modeling fluid machines with complicated geometrical passages. So, it's not just the CAD modeling, it is the grid generation which is the most time consuming process in our CFD simulation. And we also discussed that the type of grid which we would use, that is dictated by the numerical method used for numerical simulations. For instance, whether we use finite difference, finite volume or finite element method, that would dictate what type of grid we would use. And it will also depend on the requirements of flow physics. For instance, if you have got solid surfaces involved, we need to provide fine mesh close to the wall to resolve the boundary layer. So even if you are performing RANS simulations for turbulent flows over walls, we have to provide enough number of grid points close to the wall to resolve the boundary layer properly. So grid design has to take care of this aspect as well. Now we can use both unstructured as well as structured grid techniques for modeling of complex geometries. So let us have a brief look at both of these types once again. Now unstructured grids we will primarily use in finite volume and finite element based CFD analysis, and we have to follow certain guidelines to obtain good quality grid which can ensure that we can get fairly accurate numerical solutions to a mathematical model. So let us have a look at these unstructured grid guidelines. For a beginner, it would be very tempting, specifically when you are working with a commercial CFD software which will have its own built-in modeling interface where you can generate your CAD model. It also provides you a mesh generator with variety of options. So there would be a temptation to just click on one of the buttons which provides volume mesh and try to mesh the entire geometry. Now this would be what I would term as a lazy bone approach. We would be able to get a grid, but that would not be a good quality grid which we would require for our numerical simulation process. So instead of attempting to generate the volume mesh in the entire geometry, what we should do is we should decompose the complex problem domain in many small subdomains and then mesh each subdomain separately. This will ensure that we get a properly graded and good quality mesh in each subdomain. So that is first guideline which we must follow in real life CFD analysis. And similarly, to obtain a properly graded mesh, by properly graded, for instance, if you want to resolve a boundary layer, we must have very fine grid close to the surfaces and relatively cruder ones away from the walls. This is what we mean by gradation. Similarly, let us say we have got in compressible flow the presence of shock waves, the grids should be finer in those areas. So you have to provide appropriate gradation of the grid. And one more aspect which we should take care, there shouldn't be abrupt jump in the mesh size. So the gradation again should be as smooth as possible to obtain accurate numerical results. So how we should proceed? The first step would be that first generate the grid on the edges of each subdomain, then identify the surfaces of each subvolume, mesh that surface based on our measures or our requirements of the gradation, and only when this process is complete then we should attempt filling the volume of the subdomain with a grid or a mesh. So the steps would be grid the edges, from edges go to the surfaces, and then starting from surfaces obtain a volume mesh. So both of these steps or guidelines are very important: decomposition in subdomains and then a stepwise procedure for meshing each subdomain. And before we proceed further to merge all the subdomain grids, we should check quality of the mesh in each subdomain, whether it is suitable for the CFD simulation, whether the angles of different elements are within proper ranges or not. So only we have checked the grid quality in each subdomain, we should proceed further with merging them. Otherwise, once we have merged it and then we obtain the grid quality estimates, it would be difficult to regrid and re-merge the things again. In fact, we will have to do then ab initio, whereas if you have done the grid quality check at each subvolume or subdomain, we need to focus on only those subdomains where we have not got a good quality mesh, refine it or amend it, and then combine all the subdomains together. And this is a very important guideline, that we have to exercise utmost care in merging the grids of the subdomain. In fact, the care should have been exercised when we generated our subdomains by using what we call artificial surfaces. So, there are certain options which have to be chosen properly in commercial grid generation packages. Now, one of the most common errors which users make is creation of an artificial wall boundary between two subdomains while merging. So, before we do that, let us take care of this aspect, that once two subdomains are merged, they would be merged smoothly without creation of any artificial separating surfaces between two subdomains. When we were discussing finite volume methods, we saw that if you are dealing with quadrilaterals or hexahedral finite volumes, it is easier to obtain better accuracy in interpolation as well as integration. So, that is why in finite volume analysis, hexahedral finite volumes are usually preferred over tetrahedral ones due to better accuracy obtained in interpolation and integration with the hexahedral elements. So, we should try to use as much of these elements as possible. So, what we would normally do is that we would reserve tetrahedral and wedge elements, we will use them. This should be confined to the regions too complex to mesh using hexahedral elements, elsewhere use hexahedral elements. To give you example, let us have a look at two examples of unstructured grid generation, one which we performed on a locomotive model. This was a high speed train model which was given to us by Indian Railways. We had made a CFD model, this CAD model of engine, and you can see there are various protrusions involved. There are very fine geometric features which would make the process of grid generation fairly difficult. So, now, and not just this is just the solid surface which is provided by the CAD model, our actual solution domain is outside it. Now, how do we generate grid for this problem? So, this is a computational mesh, the outline here, but the green line, this tells us our what we call so called computational domain, the flow inlet and the flow outlet here, they are side boundaries, and this bright yellow green, this is our surface of the locomotive. You can clearly see that we have subdivided our computational domain into many different subdomains, and different types of meshes were generated over each of these subdomains, and then they were merged together. Now, this is one possible way of decomposition. In fact, we should decompose it in even more number of subdomains for a better quality grid. And this is one snapshot of the grid which has been obtained. It's rather a cross-sectional snapshot of the grid which consists of the hexahedral elements away from the locomotive body and the tetrahedral elements close to it, because close to it we had so many protrusions, and there generation of hexahedral elements would have been pretty difficult. So, that is why close to the boundaries in those subdomains we have got hexahedral grids, tetrahedral grids and wedge elements, and in the subdomains which are far away from the solid boundaries we have used hexahedral grid. Let us have a look at one more example. This corresponds to a highway tunnel. So, it is a long highway tunnel and it has got many adits, and these are what we call shafts for the outlet air. The air is sucked from there and discharged to the outer atmosphere, and the adits are for their what we call additional ducts through which we can access the tunnel during emergency situation. They are also used to supply the fresh air inside the tunnel. So, this is our geometry of the tunnel, and different colors which you can say here, each one represents a decomposition of subdomain. So, each color stands for one subdomain. So, this whole tunnel we have divided into many different subdomains, 1, 2, 3, 4, you can count, there are more than 10 different subdomains depending on what type of features we had at that point. And when we generate the mesh, if you are dealing with the straight tunnel portions we can go for structured hexahedral generation, but when we come to the junction points here, it is impossible for us to generate structured mesh or have a continuation of the structured mesh from both the sides. So, these are the areas where we would go for what we call unstructured tetrahedral meshes. So, this is a view of the mesh which have been generated. This is what we would call hybrid mesh, that we have got a hybrid of structured mesh on two sides and this at the junctions. So, this is shaft, the tunnel, body, both the sides we have got hexahedral structured meshes, and at the junction point we have used tetrahedral unstructured meshes. So, such things are called what we call hybrid meshes. So, these two examples which we had of fairly complex geometries, they give us a fair idea that how we should proceed about grid generation process, break our geometry overall problem domain in as many subdomains as required. In fluid machinery, the complications would be even further, even more complications would be there. So, we have to break into maybe hundreds of subdomains and then generate appropriate mesh in each subdomain and merge them together for final analysis. Now, let us have a brief look at some of the structured grid techniques. There are three structured grids which we discussed yesterday: this Cartesian grids, body feeder grids, and block structured Cartesian grids. Now, when we want to use simple Cartesian grids in the context of finite difference or finite volume analysis to represent the curved portions or curved surfaces of the problem domain, we would use what is called as staircase approximation. Now, the staircase approximation, this leads to a very crude approximation of the geometric features of the problem domain, and it might also pollute our solution. And recently, immerse boundary techniques have become very popular in the context of Cartesian grids, though these techniques originated long ago by Peskin, but recently with the advent of parallel computers, wherein use of Cartesian grids is very favorable for load balancing purposes, immerse boundary techniques have become now the flavor of the day, and lots of research work is being currently done on various types of immerse boundary techniques which can be used in different contexts. So, these immerse boundary techniques, they are based on Cartesian grids, but they permit a much better representation of actual geometry of the problem. We can have almost exact representation of the problem geometry using what we call immerse interface techniques. So, though our CFD formulation is based on a Cartesian grid, we will introduce certain features or certain forcing terms which can give the effect of the presence of curved geometric features exactly the way they were. So, programming is a bit complicated, but then we can obtain very accurate solutions using immerse boundary techniques. Not just that, these using immerse boundary techniques we can also have, or we can also exploit all the solution techniques which are developed for Cartesian grids. So, further details of immerse boundary method, or more recently is a relative called immerse interface method. See Peskin, Mittal and Icarino and Angrenstern. I have listed these references in full towards the end of the lecture. Body fitted structural grids, we have already seen that we can obtain mapping for complex physical domain onto a rectangular computational domain, and we need to solve a system of partial differential equation to obtain our grid. So, this was very popular in the beginning, but right now it has given way to Cartesian grids or block structure grids, because the transformations which we require would be very difficult to obtain if we attempt to generate a body fitted grid for a big complex problem, say for instance our turbine geometry. So, the next thing is what we can do is, instead of trying to fit in a body fitted grid for a complex geometry at one go, we can use decomposition in subdomains, and we can have a structured grid on each of those subdomains. Now, each subdomain can have different structured grid. We can have a Cartesian grid on one subdomain and body fitted grid in another subdomain, the choice is ours depending on the geometry of the problem. It is also possible for us to have Cartesian grids everywhere. So this particular technique is called block structured Cartesian grids. They are the flavor of the day very recently in context of finite difference and finite volume based CFD analysis, wherein we can have smaller subdomains with each subdomain having a different Cartesian grid, and we can have very fine Cartesian grids in the regions near solid boundaries or where we have got discontinuities or shock waves to provide a very close approximation of the problem geometry or the gradients, which are the sharp gradients which are present in the physical solution. So this is one typical example taken from Henshaw in paper on automatic grid generation published in ACTA in America. This is a full body aircraft, just one cross section of it. It's a fighter aircraft, and you can say block structured Cartesian grids. So close to the surfaces in different parts we have got the grids of various or differing densities. Close to the nose cone we have got very fine grids. Similarly near nacelle we have got very fine grids, and so on. Close to the wing surfaces or the tail surface again we have got very fine grids, and away from the body of the aircraft we have got a relatively coarser grid. So this is what is called structured, or rather block structured Cartesian grid around a complete aircraft. Such grids are very easy to generate. It is also very easy for us to divide our problem domain into a small subdomain and map each of these subdomain depending on the number of nodes we have got in that, and the load balancing on a parallel machine also becomes pretty straightforward while using block structured Cartesian grids. And this is one of the reasons why recently it has become very popular to use block structured Cartesian grids along with immersed boundary techniques, which can help us to take care of the curved boundary surfaces with almost 100% precision. This is another example of block structured Cartesian grid which has been used for simulation of a ship hull using immersed interface method by Yang and Stern. So once again you can say this background, the grid is there, the result is also put there. So we have got the Cartesian grids of different densities and close to the surfaces to take care of the presence of these solid boundaries. Immersed interface method has been used, which can give us exact representation of, or it can account exactly the presence of the curved surface of the ship hull. The next topic which we will briefly touch upon today is the parallel implementation. It is one of the most important aspects in a real life CFD analysis, and why it would become very clear that if you want to discretize a complex real life domain, say the flow around an aircraft, a turbine or an automobile, this would require a very large number of grid nodes or elements. The minimum which we have in RAND simulation is few millions. In fact, for a flow over aircraft, the typical number of the nodes would be in many billions. Now such large sized problems, they cannot be solved on the serial workstation no matter how powerful they are, because we would be dealing with very large order of algebraic equations. Okay. So in such situations we must use a parallel computer, which is typically referred to as HPC in sort of high performance parallel clusters. Now a parallel computer could be a shared memory machine wherein all processors share a large random access memory, or rather an image of it which is accessible to each processor on that parallel machine. So they are called SMD clusters. Or we can have a distributed memory cluster where each processor or node has its own dedicated memory, and these clusters, they must communicate data between themselves. Now parallel implementation of a CFD code on each type of machine would be somewhat different. Things would be slightly different for a shared memory machine than a distributed memory machine because of the memory sharing. In the case of shared memory machine, the message passing would be very small, almost negligible, where distributed memory machine there must be separate message passing interface which is to be provided, because the data at the boundary of each subdomain which is mapped to a one node, that has to be shared to the other node using message passing. So that would be one of the most important differences between the implementation on these two type of machines. However, in both the cases we have to do one thing, that is we have to break our big problem into small problems. So in either context, that is in the context of SMD or distributed memory clusters, the bigger problem must be broken into smaller sub problems which can be solved in parallel on a set of processors. Now how do you break it? That is the next aspect which we must look into. There are two popular approaches for this breakup of big problem into a small problem. The first one is called domain decomposition, that is you got big complex problem domain the way we did for our grid generation. Use a similar sort of decomposition, decompose your problem into smaller subdomains and then try to map each subdomain to each processor. And the second one is what we call grid partitioning, that is we generate a grid somehow and then this grid is partitioned using certain graph partitioning tools. Now in domain decomposition approach, we divide the problem domain into a set of non-overlapping subdomains, generate grid on each subdomain and proceed with the solution process. Ideally each subdomain would be mapped to a separate processor. It may so happen if you got so many number of subdomains, maybe many subdomains are mapped to a single processor, that is possible. So depending on the number of processors which are available on our machine, we can decide at how many subdomains we want to divide our problem into, or we can divide a problem into, let us say, thousands of subdomains, and then depending on the number of nodes or processors available, distribute a given number of subdomains onto each processor or processor core. So that is what it is. We have got a set of non-overlapping subdomains. Each processor or processor core, like recently we have got multi-core machines, that each processor might have 6 to 10 to 16 cores. Okay. So each processor core behaves like a separate processor. So each processor core or processor is assigned a subset of these subdomains which we have obtained in domain decomposition process. Now this domain decomposition process is very general, we can use it with finite element, finite difference or finite volume discretization scheme, with structured grid or unstructured grid. The next one is our grid partitioning approach. Now here people use graph partitioning tools. Two popular freely available tools are Matisse and Josel. The references are provided at the end of the lecture. And these graph partitioning tools are used to divide the overall discretized problem into a set of sub problems. By overall discretized problem we mean the total grid which we have obtained. That overall grid is broken into a subset of small grids which can be mapped to separate processors for handling. Now this grid partitioning approach is primarily used in unstructured finite element or finite volume simulations. In the case of finite differences or structured finite volume or finite element formulations, it is better to use domain decomposition method for decomposing a problem into smaller sub problems. And there is one more aspect which we must carefully take care of. Yes, we have divided our problem domain into small subdomains, and the certain number of subdomains have been mapped to certain set of processors. The care must be taken to what we call balance the computing load on each processor. Otherwise it may happen that some processors are heavily loaded, but since we are solving a problem which will cross the solution process is linked together on all the subdomains, so other processes would remain idle until the busy processors have computed or completed their part of computations. So that is why it is essential for us to do appropriate load balancing. Now grid partitioning approach or domain decomposition approach, in both the cases we have to take care of this load balancing at that level itself. And we have also got to be very careful about the choice of the solution schemes. So we have to choose those iterative schemes which can be easily parallelized for the solution of discrete algebraic systems. we cannot choose any scheme howsoever efficient it might be for a serial machine. Take for instance our early decomposition based solution process for linear equations. Early decomposition is very difficult to parallelize. So even if it were possible for us to use that, we will not use it. We have to use an iterative scheme which can be parallelized easily. So the most popular choices are the Krylov subspace solvers, which require basically matrix vector multiplications in iterative solution process, and this matrix vector multiplications, they can be what we call decomposed or distributed over a set of processors or processor cores very easily. So load balancing is very easy, or parallelizing these Krylov subspace solvers, whether they are PCG or GMRS or BiCG stab, all of these methods can be easily parallelized. The same holds good with multigrid methods. Multigrid are what we call multi-level methods of geometric or algebraic type. There are many of them which can be parallelized. In fact, their basic design itself is inherently parallel. So that's why nowadays in our commercial CFD solvers, multigrid and Krylov subspace solvers are the methods of choice for the solution of a problem, because they are inherently parallel, or they can be easily parallelized. So these are aspects which you must take care of in parallel implementation, specifically if you are writing your own code. So this way we would put a full stop to our discussions on the parallel implementation aspects and the practical implementation aspects, and we come to the end of our course. I hope you have enjoyed the course, enjoyed learning various nuances of CFD, starting from mathematical modeling to numerical discretization schemes, both for spatial discretization as well as temporal discretization, and our discussions on Navier-Stokes solutions and the solution of turbulent flows. We did not have much time in this introductory course to discuss in detail about grid generation and parallel implementation aspects, so we had a very sketchy overview of these processes. But for those of you who are interested to explore it further, explore the beautiful science of CFD, or rather science and art of CFD, it is computational fluid dynamics is as much an art as it is a science for the simulation of or solution of real life problems. I would refer you to further references. We have already seen in the course of different modules appropriate references. The references for this module for verification and validation, you can look at the AIAA guide published in 1988, guide for verification and validation of computational fluid dynamics simulations. You can also look into the textbook of Verstiger and Perek. It's one of the very compact textbooks of CFD, and similarly Versteeg and Malala-Sekharaj book published in 2007 also provides a very compact description of both AIAA and ARCOFTA guidelines. For immerse boundary method, there are many research papers available. You can look at the review paper of Mittal and Icarino published in 2005 in Annual Reviews of Fluid Mechanics, or you can look at the classic paper of Paskin in 2002 on immerse boundary method published in ACTA in America, or recent ones by Yang and Stern published in Journal of Computational Physics on sharp interface immerse boundary level set method for wave body interactions. And this particular methodology which helps us to get a near exact representation of a complex interface or curved interface. That's why it's called sharp interface immerse boundary level method. Similarly, on parallel implementation, you can look at the textbook of Barry Smith, Peter Bierstog and William Gropp, Domain Decomposition Parallel Multi-Level Method for Elliptic Partial Differential Equation. This particular book provides a very nice description of multigrid methods as well as the Schwarz methods and their parallel implementation. Then for the two grid partitioning tools which you mentioned, you can have a look at Carapace and Bipin Kumar's paper on fast and high quality multi-level scheme for partitioning irregular graphs. This is the basis of our Metis, and then similarly for Josel, you can have a look at the chapter and this contributed volume by Walsha and Cross, Josel Parallel Multi-Level Graph Partitioning Software and Overview. So thank you very much. I hope you have enjoyed the course thoroughly, and you can build on the knowledge of what we learned in this course, this introductory course, to perform well-informed CFD analysis using, let's say, commercial CFD tools, and you should also be able to write your own code keeping in view what we have learned in this course. So happy numerical analysis, and make use of the CFD techniques in solving problems in your own domain, whether they might be from civil engineering, aerospace, or chemical sciences, or even biological sciences. There are so many options, there are so many applications available for the CFD. Thank you once again.